Assalamualaikum and good day. Today we will continue our lecture session with Chapter 8 entitled AC Distributors. So let's begin with the introduction. A distribution system consists the facilities and equipment such as substation, distribution feeder circuit, switches, protective equipment, and distribution transformer that connect a transmission system to the customer's equipment. It is the part of an electric system right after the transmission line system that is dedicated to deliver electric energy to an end user. The substation itself is a high voltage electric system facility. The illustrated figure depicts the path taken by electricity through a substation. It is represented by the yellow arrows. On its path from the incoming power line, which is over here, to the outgoing line, which is over here, the electricity will flow through transformer, busbar and switchgear. Those components will change the AC voltage level from one voltage to another. Some substations are very small, with little more than a transformer and associated switches. However, some are very large, with several transformers and dozens of switches and other equipment. Basically, there are four types of substation. The first one is the step-up transmission substation. The second one is step-down transmission substation. The third one is distribution substation. And last but not least, an underground distribution substation. However, the electrical system also has substation that will combine two or more types of substation. Step-up transmission substation will receive electric power from a nearby generating facility and uses a large power transformer to increase the voltage for transmission to distant location. Whereby the step-down transmission substation are usually located at switching point in an electrical grid. Such substation will connect different parts of a grid and are a source for sub-transmission line or distribution line. Distribution substation and underground distribution substation are located near to the end user. Distribution substation transformer will step down the transmission or sub-transmission voltage to customer utilization voltage level, where the power is being distributed to industrial, commercial, and residential consumer. The following figure represents an indoor double chamber substation with a meter room. Four separate doors, door number 1, door number 2, door number 3 and door number 4, allows the officer in charge to access any one of the transformers room, which is this room and this room. These are the transformer rooms. The meter room, which is located at the back of the substation, and last but not least, the switchgear room, which is located at the middle of the building. Slides 8 represents some functions of distribution substation, where as you can see, it will change voltage level from one level to another level. It will also regulate voltage to compensate for system voltage changes. Distribution substation also function as switch transmission and distribution circuit into and out of this grid system. So let's move on to the main component of distribution substation. Basically, the main component of distribution substation include circuit breaker, feeders, protective equipment, and distribution transformers. These four components will be described in details in the following slides. Let's begin with the circuit breaker. So what is circuit breaker? So circuit breaker of a distribution substation will complete, maintain and interrupt current flowing in the circuit either under normal or faulted condition. There are several types of AC high voltage circuit breaker. The first one is the air circuit breaker, as shown by the figure in slides 10. The second one is the oil circuit breaker. The third one is the SF6 circuit breaker. And the last one is the vacuum circuit breaker. The air circuit breaker SF6 circuit breaker and vacuum circuit breaker are categorized as the oilless type of circuit breaker. Let's move on to distribution feeder circuit. A distribution feeder circuit are the connection between the output terminals of a distribution substation and the input terminal of primary circuit. The distribution feeder circuit conductor leaves the substation via underground cables named exit cable. The most common distribution feeder system topology applied nowadays are radial, loop and ring feeder. So what is the function of switches? Apart from redirect or cut-off power flow for load balancing or sectionalizing, switches are installed at a strategic location in order to permit repairing action or upgrading work on the system itself. The many types of switches include circuit breaker switches, single pole disconnect switches, triple group operated switches, and pad mounted switch gear. These are the figures of different types of switches. The first figure represents the air circuit breaker switches. Second one represents triple A break switches. The third one represents the single pole disconnect switches. And last but not least is the pad mounted switch gear. So another component of a distribution substation is the protective equipment. Whenever a short circuit, lightning strikes or other disruptive event occurs, this distribution system will be safeguarded by the protective equipment such as protective relays, cut-out switches, disconnect switches, lightning arrestors, and last but not least, fuses. By having the protection scheme, the power system is kept stable by isolating only the components that are under fault, while leaving as much as possible network to remain their operation. Under abnormal working condition, protection is vital for the safety of equipment and the safety of human being. For example, lightning arrestors. The lightning arrestor will draw the electrical energy from a lightning strike within its vicinity, so that the larger circuit breakers are not actuated. The last component of distribution substation is distribution transformer. A distribution transformer function is straightforward, which is to step down the voltage and provide isolation between primary and the secondary circuit. The transformer is very expensive and so are well protected. So how to protect it? So normally a substation transformer has minimum 3 protection. The first one is secondary overcurrent relaying, second one is primary infusing, and the third one is protection of sudden pressure relay. Apart from that, transformers are also equipped with the differential relaying bus plus a backup overcurrent relaying. So let's move on to the layout of distribution system. Figure presented in slide 21 shows that the distribution system consists of the primary distribution system and the secondary distribution system correspondingly. The primary distribution system, which is over here, would be the circuit that supply power at high voltage to the large consumer such as industrial consumer and also to the distribution substation. Meanwhile, the secondary distribution system would take the power to the consumer at the distribution voltage level. So the voltage is being stepped down to a distribution voltage level before it is being used by the consumer. An example for such consumers is the residential or domestic consumer. Due to economic consideration, primary distribution employs 3-phase 3-wire system, while 3-phase 4-wire system is viable for the secondary distribution system. As mentioned before, the classification of distribution system can be categorized according to its scheme of connection. The first one is based on the nature of the construction. The second one is based to the nature of current. The third one is according to the number of wires, whether it is 2-wire system, 3-wire system, single phase, 3-phase, and etc. And last but not least, according to the scheme of connection, which is either bi-radial, ring, or interconnected system. So let's focus on the primary distribution line or feeders, where there are 3 topology. Where the primary distribution lines can be laid. The first one is the radial primary circuit, the second one is the loop primary circuit, and the third one is the ring main system or the primary system. So let's move on to the first type of the topology, which is the radial primary circuit. In slide 26, the typical radial primary circuit scheme has been displayed. The main characteristic of a radial distribution system is that the power flow is only in one direction, which is from the feeder towards the load. It is the simplest system and has the lowest initial cost. Typically, it is applied in the area of low load density, such as in a village. Although the radial primary circuit scheme is the simplest and least expensive, it is not highly reliable. A major drawback of a radial distribution system is a fault in the feeder will result in supply failure to associated consumer, as there won't be any alternative feeder to feed the distributors. Also, extending the feeder length in order to cater more load will result in a greater voltage drop. In order to overcome the limitation of the radial circuit, the loop primary circuit provides an alternative. In the loop primary circuit, each distribution transformer will be fed by two feeders that is in different path. The feeder in the system form a loop which starts from the substation bus bar and run through the load area feeding distribution transformer and returns to the substation bus bar. This system is generally used in town and city. The loop primary circuit is very reliable as compared to the radial system, since each of distribution transformer is being fed by two feeders. Although in this system there are fewer voltage fluctuation at the consumer's terminal. However, you have to bear in your mind and you have to realize that the source of supply for the whole load system is a single secondary substation. In this situation, any failure in the supply source would cause the whole of the system to suffer power interruption. Compared to the remaining two types of topology, the ring main or network system is a more reliable system and it gives a better voltage regulation and less feeder losses. The ring main system is the most reliable for continuity of supplies. So, I have concluded three types or three different topology, and let's move on to the AC distribution calculation involving distribution systems. So as you can see in slides 33, there are several formula that were given. This formula will be used throughout the calculation involving calculation of voltage drop, current, and etc. of a distribution system. So as you can see, by taking the VB as a reference vector, where is VB? VB is located at the consumer side, which is the receiving end users. This is VB, and VA is the sending end voltage. It can be concluded that all of the distribution calculation involving voltage drop and so on does apply the Ohm's law, the Kirchhoff voltage law, and Kirchhoff current law. So therefore, formula given in this page are for references only, and you don't have to memorize all of it. So let's move on to example 8.1. In example 8.1, a single phase AC distributors of 300 meter long is fed from an A and is loaded under 100 ampere at 0.707 power factor lagging, which is 200 meter from point A, and the second load is 200 ampere at 0.8 power factor lagging 200 meter from point A, and you have to calculate the total voltage drop in the distributor. So in order to solve this problem, first of all, you have to illustrate the AC distributor systems, which has 300 meter long and load C is located 200 meter from point A, while load B is located 300 meter from point A or 100 meter from point C. So in order to solve the voltage drop across the distributor, which is VAB, you have to calculate VAC and VCB first. So in order to solve this problem, first of all, you have to find out what is the value of I1 and I2. It has been given inside the question. So I1 and I2. From there, you have to calculate the voltage drop at section VCB by simply applying the Ohm's law. Later, you have to calculate the VAC. How to calculate VAC? Just simply apply the Ohm's law as well. But before that, you have to calculate the IAC first, which is over here. How to calculate IAC? You just apply KCL at node C. So IAC is equals to I1 plus I2. The voltage drop in the distributor is equals to VAC plus VCB, or you just simply apply KVL from this point up to this point. So at the end, the voltage drop in the distributor is equal to 17.44 minus J 3.81 volt. When you convert it into polar form, the magnitude of the phasor is equal to 17.85 volt. So let's move on to example 8.2. In example 8.2, a single phase distributor of 2 km long, it is 2 km long, supply a load of 120 ampere, 0.4 factor lagging, it is over here, and another load is located at the middle point of the distributor, which is at 80 ampere and 0.9 power factor lagging. The voltage at the far end, which is the voltage at point B, is maintained at 230 volt, and you have to calculate the voltage at sending end, and also you have to calculate the phase angle between voltage at the two, and so you have to calculate the voltage between two ends, which is voltage and the angle between point A and point B. Same technique as before is applied, which is the first one is you have to find out I1 and I2 in order to calculate voltage drop across VCB and VAC. In order to find the voltage drop across VCB, you just simply use the Ohm's law by multiplying I2 with the impedance across point C and B, which is ZCB. This would give you 12 plus J6 volt. Later, once you find out the value of IAC, which is just simply apply KCL at node C, which is by adding up I1 and I2, you can use the Ohm's law in order to calculate VAC, where VAC is equals to IAC multiplied with ZAC, which is the impedance across point A and point C. In order to calculate the sending end voltage, you have to apply the KVL at this loop. So VA is equals to VAC plus VCB plus VB, which equals to 261.08 plus J17.45. So when you convert into polar form, you will get the magnitude of VA is equals to 261.67 with angle 3.82. Since we took VB as the reference voltage, so whatever angle that appear in VA is equals to the phase difference theta between VA and VB. So let's move on to the tutorial question. A single phase distributor of 1 km long has resistance and reactance per conductance of 0.1 and 0.5 ohm respectively. At the far end, the voltage BEV is maintained at 200 volt and the current is 100 ampere at 0.8 power factor lagging. At the midpoint of the distributor, a current of 100 ampere is tapped at power factor of 0.6 lagging with reference to the voltage F at Vm. So for this tutorial, you have to calculate the voltage at the midpoint, you have to calculate the sending end voltage, and also finally you have to find out the phase angle between VA and VB, which is the phase angle between sending end voltage and receiving end voltage at point B. So in order to solve this problem, you have to first of all illustrate it. So this is the distribution system, distributor. So this distributor is 1 kilometer long. So at the midpoint, which is 500 meter away from point A, is point M. We have 100 ampere 0.6 lagging load, and at point B we have 100 ampere 0.8 lagging load. Both of the load are lagging load. So the impedance as given by the question, it is equals to 0.1 plus j 0.515 respectively in each section, which is ZAM and ZMB. So voltage VB is maintained at 200 volt, or simply in polar form 200 angle 0. So the first one, you have to calculate the voltage at the midpoint. So in order to calculate the voltage at the midpoint, you just simply apply KVL across this loop. So Vm is equals to VMB plus VB. We know that VB is equals to 200, so you have to calculate VMB. The only solution to calculate VMB is by applying Ohm's law across point M and point B. So just multiply the current. So IMB is equals to IB, so multiply with the impedance. So the voltage at point B is equals to 217.J6. So this is, in section MB, it is equal to 17 plus J6. So the voltage at point M, as I mentioned before, you have to apply KVL. So Vm is equals to VMB plus VB. So just add up these two voltages. So 200 plus 17 plus J6. So you will get 217 plus J6. Or you convert it into the polar form. So the angle is 217.1, where the angle is the magnitude is 217.1 and the angle is 1.58 degree. So let's move on to the second part of the question, where you have to calculate the sending end voltage, which is VA, and the third one is you have to find the phase angle between VA and VB. Differ from example 8.2, in this tutorial question, you have to apply KVL at this loop in order to find VA, which is an alternative solution approach as compared to example 8.2. In example 8.2, VA is equals to VAM plus VMB plus VB. But in this example, since VM, we have already calculated VM, so VA is equals to VAM plus VM. So how to calculate VAM? First of all, you have to apply KCL at node M, where IAM is equals to I1 plus I2. So VAM is just simply applying the Ohm's law across this point, which is IM multiplied with ZAM, and the final answer is 34.96 plus J7.5. The sending end voltage is equals to VAM plus VM. What is the value of VM? We have calculated the value of VM at the first part of this question. So 217 plus J6 plus 34.96 plus J7.5. So the final answer for the sending end voltage is equals to 251.96 plus J13.5 volt. Or you may simply convert it into polar form, and the magnitude of the polar form represent the magnitude of the phasor V A, which is equals to 252.32, where the angle of the polar form of BA, which is 3.07, we simply provide the phase difference theta between BA and BEV. Why? Because we set VB as the reference voltage and VB has 0 angle. So theta A minus theta B, 3.07 minus 0 equals to 3.07. So that's why we can simply take the value of theta A as the phase difference between VA and BEV, or to represent the phase difference between VA and VB respectively. In conclusion, the supply voltage at VA is 252.32 and its phasor will lead VB by 3.7 degree. So with that, I have reached the last slide for chapter 8, and consequently this is the last topic for the course. All the best for your final exam. Study smart and stay safe. Thank you very much.